Today's experiment, we're going to be looking at the wave nature of light specifically. So when we're studying things like how lenses work, that could be explained with both waves or an alternative theory that we'll learn soon. But today we're going to do experiments that show that light has to be a wave. Now, before I get started, Caitlin, thank you for reminding me. Back, Caitlin. The posters for the lab projects need to be turned in by Friday, April 14. So make sure you have that in mind. I didn't know at the beginning of the semester what the date was, so it's not in the syllabus. But that's when those are due. The reason it has to be due then is because when we need to get them to the printer to get them back, we need to do them before they come to their dead week at UNL, because we're having them printed by UNL and they have too much of their own business and they can't print for us if we wait any later. Actually, before their dead week. Yeah, that's right. We're getting close to the end of the year. Can you believe it? Okay, so talking about wave particles. We talk about the nature of light. Probably the most famous of our early physicists would be Isaac Newton. And Isaac Newton believed that light was a particle. He called his theory about how light worked a corpuscular theory, that we have these little corpuscles of light that were like balls. And he explained how refraction worked with this corpuscular theory, incorrectly, but he explained how it worked. And everything was good. And I mean, he was Newton. Who's going to doubt Newton? You know, I rarely doubt the man. Gabriel's a little braver than I. He just hasn't been indoctrinated like I have, is the thing. But then Thomas Young comes along, and Thomas Young does an experiment like we see on the screen here. In that experiment, he first uses a single slit to make incoherent light so it behaves like it's coherent. Using that single slit, you just get a little piece of the light, and then that light is generally going to be closer to coherent. And then he had the light from that single slit go through two different slits. And what he found when the light went through those two different slits is not what you may have expected. So I'm going to use a laser here to recreate what he did. Maybe. We'll see. First, I think I have to plug the laser back in. Turn on Sesame. Come on. I must have turned it off. Yeah. Okay, so there we have the laser dot. Everybody see that dot? Now I'm going to turn off the projector and turn off the lights, now that we've got everybody here. And have the light go through maybe a pair of slits. Or maybe not. Well, there's another option. By the way, you all know you don't get your head down there and look into the laser. Okay, it's going through two slits right now. And if you look up here, you see a pretty complex pattern. Now, Newton has said light behaved as a ball, as a particle. And if I throw a ball and I have a picket fence that has two slats out, if the ball goes to that picket fence, it's going to go through either one slat or the other, right? And then if I have a fence behind there, where the ball is going to pile up on the fence behind there, what are we going to see? Yeah, we see two piles. One for the balls that went through this one at that direction, one for the ones that went through this direction. That's all we would have. But here, going through two slits, we see a complex pattern. That cannot be explained if the light is traveling as balls. And so the particle theory, the corpuscular theory of Newton, was definitively disproven, right? This was an experiment that could show that light's not a particle, and indeed, it showed light's not a particle. This is consistent with light being a wave, because you probably have sat and watched the ocean waves go by, and they hit a jetty, and they bend around that jetty. Everybody experienced something like this? Well, 3 of us have. I guess the rest of you are going to have to take it on faith that when a water wave comes and hits a breakwater, it will bend around that breakwater. And we call that diffraction. Diffraction is the light bending around an obstruction. It occurs with water waves. It occurs with sound waves. That's why you know that if I opened the door, walked outside, went around the corner, and left the door open, you'd still be able to hear me because the sound waves would bend around. And so the waves would bend around. So if I have waves coming through each of these slits, they'll bend around and come out going in all directions. And as we talked about in class this morning for the people in Physics 252, I almost said a little tall. This would be, what is his name? Oh, guys, my went blank. Yeah, Huygens principle. Huygens principle that says that we can treat each spot on a wavefront as a new point source with light going in all directions. So the light goes in all directions coming out. But when that light comes out in all directions, I want to show, okay, I just don't have the picture for it, so we won't go 20 slides forward to try to find it. You're going to have situations where you have constructive interference and destructive interference between the light that went through one slit and the other slit. What's our condition for constructive interference? They're in phase. In phase means that they have their peaks at the same time at the same location. And if you shift by 2 pi radians or 1 wavelength for the path length, you'll be back in phase again. So it recurs, so there's multiple differences in path lengths that will give you the in-phase condition. Now, just to look at the phase conditions, here are 2 waves, the green wave and the blue wave, that are in phase. They are both reaching their peaks at the same time. And so the amplitude of the electric field is the sum of those 2. So we have a stronger wave, a stronger electric field, and the intensity is power per unit area, which means energy per time per unit area. The intensity of the light is what we perceive as how bright it is. That's why we talk about the intensity, because it deals directly with our perception. The intensity is proportional to the amplitude of the electric field squared. So if I have 2 waves and they're in phase, the amplitudes add up. So if I have wave 1 with amplitude 1, wave 2 with amplitude 2, if they're in phase, I'm going to have the 2 add up to give me a wave with amplitude that's equal to the sum of those 2. So to calculate the intensity, I square that. So intensity is equal to that constant C. That C just means it's proportional to, so it's constant proportionality. A squared, which putting in A1 plus A2, I know you find this funny. It wasn't until I came to Union College that I learned the whole FOIL thing. All through high school, grade school, whatever, we just learned to multiply them together. But when you do that, you have this one squared plus this one squared plus this one times this one plus this one times that one. So you have this long thing here. And if you break it down, this last term could be written as 2 square root of CA1 squared square root of CA2 squared. That would be the same thing. And so that's what's been done here. The square root of I1 and times the square root of I2. And so the intensity you have when they're in phase is the intensity of the first one plus the intensity of the second plus 2 times the square root of the products of the intensities if they're in phase. So the intensity is bigger than just adding the intensities. Is that surprising? Yeah, to me it is, because I know energy can't be created or destroyed, and my brain then says intensity should remain the same. But in fact, since intensity is proportional to energy squared, the energy staying the same actually resulted in a higher intensity. Well, now let's go to, this is just summarizing what we did. These are out of phase. It's destructive because one's at a peak when the other one's at a minimum. Oops, I did the wrong one. It's the green and the blue. The green's at a peak when the blue's at a minimum. You add them together and you get the red. the amplitude of the red one is smaller than the amplitude of the biggest one, by definition. And so the question is, what's the intensity going to be here? How would we calculate the intensity now? First start with what's the amplitude? Say louder, please. No, the amplitude, yes, of the red one, the one that's the two combined. Oh, okay, I see what you're saying. You're reading a number. Okay, that is correct. I wanted the equation of it's the amplitude of the blue one minus the amplitude of the green one. That's what I was looking for, but you're absolutely right that 3 is the amplitude, right? Because it shows it right there. So that's my amplitude. So that means the intensity is equal to CA squared is equal to C times A1 minus A2 quantity squared equals C times, and what do I get when I multiply A1 minus A2 by itself? A1 squared? And finally, plus CA2 squared. How is that different from the intensity when they were in phase? This term here is the same, right? This term here is the same. What's different about the middle one? It's minus 2 square root intensity 1, intensity 2. Now, if the two had the same intensity, then this would turn out to be 0. Because square intensity 1 times square intensity 2 would just be intensity. And so I'd have intensity minus 2 intensity plus intensity would be 0. So if they have the same amplitude, it would be 0. If they're not the same amplitude, well, you have to use this. So there's our result for destructive interference. We have that minus sign. Now, just to make sure we understand constructive versus destructive, don't use your clickers. I don't have the computer running. Just blurt out, in the figure, are the two sound sources coherent? What does it mean to be coherent? Okay, it actually means, does it have a fixed phase relationship so it's not varying? It doesn't actually have to be inherent in phase to be coherent, but it has to have a fixed phase. So it has to keep the same relationship. So when it's coming out of the speaker, we can look at the past history to say, did it keep its phase relationship over time? Okay, so the answer there was yes. Not no, not part of the time, because if it was part of the time, we would have had somewhere where it broke. With the laser, that's actually what happens when we change from one wave train to another wave train. Suddenly, you have a break in the sine wave and it starts over somewhere else. At some locations, well, no. Now, when it gets to the young lady here, or maybe older lady, compared to me, she looks young, is it constructive or destructive? How do you know? One's a maximum, the other's a min. That's the definition of destructive. So we went through the conditions for constructive and destructive interference yesterday. If the path length difference is an integer number of multiples, it's going to be constructive because they're going to be, they start in phase and one has one wavelength longer path, they're going to be back in phase again because they're just shifted by that path length difference. And so in that case, they're in phase, they interfere constructively. And if it has the half integer, then it's going to be destructive. So how does that matter to us? I'm going to skip over this slide. It gives us conditions for constructive and destructive interference. This here is a problem I'm not going to do, but I'm going to just go through the theory. We have a microwave. This is basically, well, yeah. It's kind of how a radar detector works, except for the radar detector, you have that M is moving, and it measures the shift in frequency rather than constructive and destructive interference. But you have a microwave emitter that's sending out waves. They hit a reflector and come back. And then if you have a second reflector that's a bigger distance, the waves have to travel 2 times that distance, right? That's additional. So the path length is 2x additional. So L1 is 2D, L2 is 2 times D plus X, or 2D plus 2X. The difference in path length is 2X. And what's the condition for constructive interference? If delta L is m lambda. So we can look at this and say that means that if 2x equals m lambda, therefore lambda is equal to 2x over m, where x is the distance you move and m is how many times you went from constructive to destructive to back to constructive. So this has a picture that goes with it. Here's constructive interference. Here's constructive interference. Here's constructive interference. So I can take this and say, okay, my x changed from, what would you say, 3.8? Okay, 3.9. I'm good with that. Plus or minus, of course, 0.1 there. And out here, right about 6.5, right? And so that means I have, what's my M, what's the difference here in the number of peaks? So I'm going to use in that equation, wavelength is equal to 2 times the distance here. The difference is 6.5 minus 3.9, which is 2.6, divided by the number of cycles we went through, which was 2. And we could determine the wavelength of the microwave light. I wasn't going to do it, but I did. Because the student asked me about the difference in DVDs and CDs yesterday, I left this in. A CD, a DVD, a Blu-ray, they're all fundamentally the same thing. You have a laser beam that shines into a disc, reflects back out, and you look at the interference between the light you sent in and the light that you sent out. If it's a printed DVD or CD or Blu-ray, then you just have the picture that you see on the left. You have an aluminum layer that reflects light, and the height of that aluminum layer varies. And then you have a constant thickness acrylic covering it. Now notice on the back side here where the red it says label, that's where it says, Van Halen 5150 or whatever. That's where it gives you all the information about the CD. And that is not part of anything that has to do with the data, fortunately. So you can mark up that side, scratch it. It's not going to affect anything unless you scratch the key. But on the other side, you have a difference in the thickness of the light going through the acrylic. And so you're going to have a shift in wavelength depending on if you're at one of the lower sections or one of the higher sections. And then your laser is sending out, bringing back the reflection, and interfering the two together to see if it's constructive or destructive, and that's how it reads the disc. Now that begs the question, what's the difference in a CD, a DVD, and a Blu-ray? The CD and the DVD, I'm not sure exactly what the difference is. I'm pretty sure the DVD has a higher density. They might use a different color laser for that. The Blu-ray, as the name implies, uses a different color laser. It uses a blue laser. Why a blue laser? Blue lasers have a shorter wavelength. Having a shorter wavelength means that you have better resolution because you have less diffraction, something we're going to talk about at the end of today's lecture before the lab. And so the Blu-ray can pack information closer together because you're using a blue laser instead of using like an amber laser that you use with a CD. Also, you should be aware that most CD, DVD drives these days don't use a single laser as shown in this picture. They use a couple lasers at different angles. So if you have a scratch, one of them hopefully is not going to be hitting the scratch and you can still read the data. So it gives you some error correction and you can have little scratches and it still works. Oh yes, and Blu-rays actually have, this picture is not showing it, but it reminds me, they actually have multiple layers. They have, you see here a lens to focus well, this is the detector, a lens to focus the light. They'll focus the light to different depths to read the different layers, which is kind of cool. All right, back to Young. Now that we've gone through a little primer, Young found multiple spots that could only be explained by a wave nature, where you have constructive interference at different angles. And so using geometry, Young, and every physicist who's ever taken physics class, was able to determine that if the screen is far away compared to the separation in the slits, then these two rays are essentially parallel. Now, in my picture, that doesn't look parallel, right? Everybody from this morning remembers me saying, yeah, we're drawing it for close range, but this is supposed to be far field. So this distance, D, might be, let's say, 10 centimeters. And this distance, lowercase d, might be 1 micrometer. Well, 10 centimeters is 100,000 micrometers. So if you compare these two numbers, capital D is much, much greater than lowercase d. And that's the condition where this then becomes true. Because if you make a triangle, and this side of the triangle here is very small compared to these two sides, then this angle alpha here is approximately 0 degrees. It'll never be exactly 0, but it's approximately 0. And so if I cut this off square with the center line, then these two angles have to be equal and have to be 180 degrees minus 9 or minus 0 degrees, and then divide by 2 because there's two of them. Well, 180 divided by 2 is 90. So what we have here is the mythical 90-90-0 triangle. It's not truly 990, it's more like 89.99, 89.99, and 0.01. But who's going to argue about that? So in that case, then this line here is cutting this off so you have a true isosceles triangle. The left side and the right side are equal in length. And so the difference in path length from point A and point B is 0. And the difference in path length from the slit to the screen is just going to be this side of the triangle. And then we just use trigonometry. We have a right triangle. The hypotenuse is lowercase d. The path difference is the opposite side. So sine of theta is equal to delta L divided by d gives us delta L is lowercase d sine theta. So that's how we get the length difference. From class yesterday, we learned constructive interference occurs under what condition? Constructive when delta L is equal to an integer multiple of a wavelength. And so using this relationship, delta L is equal to d sine theta equals m, that's a lambda, not a y. That's my condition for constructive interference. And then what about destructive? Right, delta L equals m plus 1/2 wavelength. And so delta L is equal to d sine theta equals m plus 1/2. There's my condition for destructive interference. So one of the two things you're doing in lab today, for lab today you have two hypotheses, and you're not making them up. Hypothesis number one is that these two equations that I wrote, and actually you're only going to need the top one, the constructive interference one, describes where those dots are we see when we use a diffraction gradient. Now what I showed you before, I used a single double slit. I used two slits to make the pattern right here. That's very complicated, right? Well, let's go with what we call a diffraction gradient. What you're going to use something for your experiment, something like this. Stay there, Sesame. You see this spot, and then you see this spot, and then you see this spot, and so on. So your observation would be, when I use a diffraction grating, I see that instead of just one spot, I see a number of spots at very specific locations. And this should be explained by the equation, blah, blah, blah. You don't have to go through the derivation we just did, but by the equation that was just on the screen. Let me ask you a question. Why does this have distinct spots, whereas the double slit didn't have distinct spots? It had them kind of fatter and not just a distinct spot. Any ideas? Gabriel.
The space between the slits is really, really small.
Well, that is true, but it's not actually the full reason. So let's get to the full reason. I think I have the full reason here. Okay. Yeah, here we go. So if I have multiple slits, then I'm going to have multiple paths, and I'm going to once again use the separation between adjacent slits. Now that D is kind of truncated. When I put this together, I wasn't careful, and I should have put this on top, and I didn't. So that D was covered up by the box with text in it. So the D is the separation between each individual slit. And so now I have all of the different slits giving me points of constructive interference. And because of the work we just did, we see that each one is going to be constructive at the same angle. So that they all of the slits will be constructive at the same angle, giving us the bright spot. If you move away from that angle, the path length changes are different for each slit. And because the path length changes are different for each slit, as you move away from that spot, you very quickly, as at a very tiny angle, get to completely random phase differences. And if you get to random phase differences, it averages to 0. And so with the multiple slits, you have destructive interference everywhere except the points where you have constructive. And that's why you have the distinct points instead of a broad region of bright. So when you're making a spectrometer, you use a diffraction grating with a large number of slits so that you'll have distinct spots. So once again, for maxima, it's the same equation we had before. What is D? It's the separation between slits. Now, if you look at this grating that I have here, it says 13,400 lines per inch. How do I find D? Okay, so the first thing I'm going to do is I'm going to say, well, let's take this and convert it to lines per meter. So we have 1 inch equals 0.0254 meters. And so that will give me the number of lines per meter. Somebody actually want to do this for me? I'm kind of curious. By the way, that 0.0254 is an exact number. The inch is based on the centimeter. No longer based on anybody's foot.
527,559 lines per meter.
Yeah, per meter. I was thinking per centimeter. I'm all that ain't right. Okay, 527,000. What is it?
559 lines per meter.
So it's that many lines per meter. That means the separation between them is 1 over 527,559 lines per meter. So what's 1 over that?
1.896 times 10 to the 6th. -6.
Yeah, I was like, whoa. Okay, so the separation here is just a little bit under 2 micrometers. Right? That's a really small separation between the slits. Okay, so for this part of the experiment, remember, if you look through, which you should have because you have the pre-lab quiz, that's the whole point, so you look through. You don't have a specific guide for how you're going to do the experiment. You need to figure out how you're going to do the experiment. Well, let me give you a couple guidelines on how you're going to do it. Number one, make your measurements from both sides of the 0 point. Don't just make a measurement from the center point to like m equals 1 bright spot. Make the measurement to m equals 1 bright spot and to m equals minus 1 bright spot. Because if you have your geometry a little bit off, if things aren't square, it'll mess you up if you only do one of them. But if you do both, then you can average it out. So make sure you measure on both sides. You might try using the first order and the second order to get two different measurements just to make sure that they are consistent with each other. You're going to be using a laser. I have out here 1, 2. This is my best laser, but it's also the hardest one to use because it doesn't have magnets on it. It doesn't sit nicely on your table. There's a third one. There's a third laser somewhere here. Oh, 2 of them in the back table. So we have a total of 4 lasers that I got out. So you're going to have to take turns doing this. So some people will, 4 groups, will want to start doing the one with the laser first so that they can get it done and other groups can do it after them. The other groups will want to start with the other part of the experiment. So, you ready to move on to the other part of the experiment? Yeah, me too. I do have to point, okay, this is, if you use white light, it breaks the light up into the distinct colors. So let's just observe this and have a little fun break before we go to the next topic. So I think I passed these out once before, but here's where we're actually using them for real. So take one down, pass them around, you know the drill. And of course, one for me. And I'm going to get some light sources set up while you are passing those around. So, number 1. Okay, does everybody have their glasses yet? I'm trusting that I won't knock that over. And I need to do a couple more things to make it nice and dark. All right, here we go. So I have this light bulb, and I'm going to warm it up just a little. So now if you look at it without the glasses, you just see an orange filament, right? But you put the glasses on, and what do you see? See an orange filament in the center. What do you see out to the side? Okay, if you're too far away, come on up so you can see, because I do want you to actually be able to see this and observe.
Oh, there you go.
Oh, no, I see that.
That's right, just.
Yeah, not too much.
Oh.
Oh, I'm so sorry.
Okay, so what do you see when you look off to the side?
Rainbow.
A rainbow.
Okay, a rainbow. What is the color that is closest to the filament?
Red.
Blue?
Violet.
Yeah, I'm going with, actually it is blue. The closer the filament is blue, you get further away and you've got green, yellow, red. Not much blue there though, right? Now if I make it hotter, you notice the color changes. It's no longer as dark an orange, and now you see a lot more blue, right? Now, one of the laws that we haven't learned is the Stefan-Boltzmann law that says the amount of light that's produced is proportional to the temperature raised to the 4th power. So if I double the temperature, it puts out 16 times more light. So a little bit of raise in temperature makes a lot of difference in the amount of light. Another one is Wien's law, which says that the peak wavelength, the wavelength that has the strongest, is inversely proportional to temperature. So when it's hotter, you get shorter and shorter wavelengths that are peak. What color is the shortest visible color? Violet. So we should be seeing the brightest in this rainbow moving toward violet as it heats up. So let's go hotter. And you see what's happening in the blue and violet range? It's definitely expanding there and becoming brighter. And believe it or not, I can actually that's made for 120 volts, but now I'm putting 135 volts through. So we have a continuous range of colors here, and we can separate them with these slits. Why? Because different colors, different wavelengths are going to have constructive interference at different angles. Now, this is one way of producing light because it's hot. Now we have a second way of producing light, and that's what we call the line spectrum. So this here, I believe, is hydrogen gas. I have to come out here to make sure. Actually, I believe that's helium. Hydrogen would be more of a bluish pink, not having that big yellow line in it. You see here very distinct colors. This is important. We're going to be studying quantum physics coming up real soon. This indicates that there's only certain colors produced, and this is what got Einstein a Nobel Prize. So we have only distinct colors, which will translate when we learn into only distinct energies, which means that electrons can only have distinct energy levels in atoms. Until this experiment confirmed it, people thought electrons could have any old energy state in an atom. But this experiment showed conclusively, no, they can't have any energy state. We can study those by using these diffraction gratings. Now, you might notice these diffraction gratings have not just one, but you have all around different things. That's because it has a grating going horizontal and a grating going vertical. And the horizontal and vertical combine to give you ones in the diagonal as far as the diffraction patterns. Okay, this is our show and tell on this part. Anyone got questions about it? Okay, let me turn the lights back on. And we're done with half of the show and tell for the day. The other half is, by the way, my favorite part of any lecture in any physics class. Just so you know. So that is our understanding of diffraction. I have skipped one section. I've skipped the diffraction from a single slit. There is in here information about diffraction from a single slit. And it has the interesting fact that you have dark fringes that are broken. There's a bright fringe in the center where the pattern would have the dark. But we have to do some more work to figure that out, and we're not going to. So let us move on. Oh, I do need to cover this. I talked about telescopes and getting the biggest objective you can because it gives you two things. Number one is the most light gathering power. Number two is the best resolution. Here's why. If you have a circle, you have diffraction around the edges. You always have diffraction on edges. Doesn't matter what the shape is. And so a circle has diffraction. So if I have a telescope with a circular objective, there's going to be diffraction around the edges of that circle. And so the diffraction pattern, now the work is much harder for a circular hole than it is for the straight edges like we did. But you have a diffraction pattern. So this is showing the diffraction pattern from a circular object. This is a circular hole. You have the center. This region here is the light at the center maximum. And then you have another, other bands going out. Because of that, you have differing sizes of the variation that gives us our resolution limits. One thing I should have pointed out, we had d sine theta is equal to m lambda. That is the spread of the light, theta being the spread, is proportional to the wavelength and inversely proportional to the size of the opening. If I change this to sine theta equals m times lambda over d. This was for bright, or I'm actually going to go back to the right place so I don't, obviously I know this, but sometimes my brain goes bonkers because there's a difference between the single and the double slit. So for the single slit, which is what we worked out, we had maxima for d sine theta is equal to m lambda. So we could rewrite that as, I keep looking for a single slide, the one I did the work on. Well, this one here has the answers. So for the double slit, you have sine theta equals m times lambda over d for constructive, and you have sine theta is equal to m plus 1/2 lambda over d for the destructive. So we can put this into a very practical sense if we go to the single slit. The double slit's not as practical for what I want to talk about. If we go to the single slit, this question here is what I'm going to talk about, but for the single slit, go to the single slit. The result of the single slit was you have destructive interference Now, we didn't do the derivation at a sine theta equals m lambda, where a is equal to the width of the slit. So sine theta is equal to m times lambda over a for destructive. In other words, the distance between here and here is proportional to m lambda over a. So if I want to make it have a narrower slit, what should I do to lambda? Make it smaller. Or what should I do to the opening? Make it bigger. So those are the two things that would give me a smaller peak, a more distinct, better resolved peak. Now, if we go to a circle, it turns out that we have a similar relationship. It's a sine theta is equal to, for the first one, remember we had the m's, m equals 0, 1, 2, 3, 4. This one here is for the first one, the lowest value you would get. And so that gives us sine theta is equal to 1.22 times lambda over a. Once again, how are you going to get a smaller angle? Either wavelength is smaller or the aperture size is bigger. So that's why you have better resolution with a big opening on your telescope, and why you have really poor resolution with a radio telescope because the wavelength is really long. Now, a practical problem. We're at the fairgrounds. At the fairgrounds, you've seen the speakers that I'm going to draw it diagonal just so I don't bias anything. Speakers that are shaped like this. Have you seen those speakers? Have you ever wondered why they're shaped like that? If the answer is yes, then you're in the scientific mode, because the scientists are wondering why they do that. If I have a narrow opening like this, what's that going to do to the central maximum for diffraction? If it's a narrow opening, the central maximum becomes bigger. So this is having the sound spread out big this direction. If I have a broad opening, what's that going to do to the spread of the sound? It's making it smaller. So this one here doesn't spread much. So now we're at the fairground, and I have a speaker in the center of the fairground. Where do I want my sound to be focused? I want it on the ground. I don't want to be sending it up into the sky. So that means for my vertical range, I don't want much spread. But for my horizontal range, I want to hit everybody in the fairground. So which way should I have that oriented? Should it be oriented like this or like this? The first one, and you know that because got the big spread horizontally and the little spread vertically. Every now and then you'll see one mounted like this, and all you know is, well, that person doesn't know what they're doing. Somebody said put it up, and they said, well, I'm going to put it wide so it covers a wider range. But that's the opposite of what it really does. Okay, a last thing on this, Rayleigh's criterion is a criterion that we use to estimate the smallest detail you can see when using a telescope or microscope. And his criteria says that if we have two peaks so that the, actually, I drew this a little bit off. Come on, erase. So the minimum of one falls at the maximum of the other. That will be able to resolve. We'll be able to see if there are two peaks. If they're closer than that, they're going to add up and it'll just look like one broad peak. So that's Rayleigh's criterion. That's what we use to actually distinguish, can I resolve something or not? So of course, this angle here is that theta that came from the equation a sine theta equals 1.22 lambda. And so the resolution, the smallest thing you can resolve is going to be the angle you get between the center and that first minimum. That's Rayleigh's criterion. So it sets a reference point for what you can resolve.